organisers for inviting me. It's a pleasure to be here. And so today I'm going to be talking about gravitational waves into city space-time. This was a piece of work I did before the announcement. And what it's about is, well, it's gravitational waves are normally represented mathematically as though we're in an asymptotically flat space-time. And the theory for that is very well developed. But over recent years it's become obvious that our universe is not asymptotically flat, it's undergoing an accelerated expansion. And so one should actually consider how gravitational waves behave in such a space-time. Right, so, I mean, the bottom line, well, the first question that one asks is it going to make any difference as far as a gravitational wave detector is concerned? And the answer is no. And we'll see why as we go through it. But what also comes out of this is that it actually raises some interesting questions about fundamental physics. It's to do with conservation of energy, and we'll have time to discuss that at the end. But I mean, one needs to see the results before one starts talking about it. So, actually, this whole question was first raised by Ashtikar and others in a series of papers last year, and also in India by Dayton Hock. So there've been a whole series of papers on this issue because obviously with detection of gravitational waves becoming imminent, the question as to whether the cosmological expansion would affect predictions is clearly an important question. All right. So what I'm going to be talking about, if anybody's interested in following it up further, just look for me in the archive at the end of last year or FISREV D, the beginning of this year, and you'll find it there. And then some of the background on which this is all based is a paper I did in 2005, and some of the ideas actually go back a lot. Right, so just to give an outline, first of all I'll be looking at the Bondi-Sachs formalism, and then we'll spend a little time looking at linearized solutions about Minkowski and the Bondi-Sachs formalism, because that provides really what one might call the standard framework for understanding gravitational waves far from the source. I mean, formally it's described, I mean, not that we need to go into that. I will also look, because the way I want to look at this is what one might call in a very specific or physical way. So we'll look at the example of gravitational waves from two equal masses in circular orbit in this formalism, and one can, I mean, not surprised, one can come up with an exact solution. Then what we'll do is generalize this solution to de Sitter space-time and look at the properties of gravitational waves in de Sitter space-time, which are then technically a little bit more complicated than Minkowski. So it's useful to understand that first. And then we raise the interesting questions about fundamental physics. All right, so the idea of the Bondi-Sachs approach is that one has a coordinate system that is based on outgoing null cones. Right, so I mean there are different ways one can do it. One can look at having a time-like geodesic and then in a sense hanging the coordinates based on that time-like geodesic. So the coordinate system is very physical. You can think of some time-like geodesic, and every second you flash a light, and as these light rays propagate throughout space-time, they define the coordinate system. So along each light ray, the angles defined in the neighbourhood of the geodesic stay constant on the light ray. The time at which from the geodesic the light rays emitted stays constant. All right, all that varies as you go out is R, which is a surface area. So it's defined by the condition any surface of constant U and R has area 4 pi r squared. All right, so the metric is then totally general and takes this form. So it has these metric potentials, beta, WC, UA, and HAD. All right, to put this into perhaps, I've used here generalized angular coordinates, but if you'd rather think of this as being spherical polars, that's fine. Okay. Okay, but because we're dealing with a surface area coordinate, we have this condition that the determinant of HAD is the determinant of the unit sphere. Right, and then to perhaps reduce this to a more familiar example, Eddington, Finkelstein, and Minkowski. Well, if we put beta equals UA equals 0, HAD equals QA being WC minus term over R squared, we have the Eddington-Finkelstein metric. And we put WC equals 0, we then have Minkowski. Okay, so it's just, in a sense, it's a generalization of that. And we can introduce, all right, this quantity HAD has only got 2 independent components. I mean, it's a 2x2 symmetric matrix, but it satisfies the determinant condition. So there are only 2 independent numbers. So it's convenient to represent it by one single complex number. We won't need to go into the details of that. So, I mean, for now, if you're not familiar with that approach, we can just say that J is a complex number that represents HAD, and it represents the deviation from spherical symmetry. In a spherically symmetric case, J is 0. And J is directly related to the gravitational wave polarization states H plus H plus. And again, I'm not going to go into those technical details. So what happens is that Einstein's equations can be take this convenient hierarchical form, that they can then be categorized like this, where the Fi include hypersurface derivatives. So given J on a null cone, the equations can be solved hierarchically to obtain the metric throughout the cone. Then one has this evolution equation, which will then give you J on the next. All right, and then we have the constraints R naught alpha, which I'll come back to. Right, so in numerical calculations, we use a compactified coordinate so that R equals infinity is represented by Z equals 1. And this then becomes a well-defined evolution. Okay, and actually this evolution problem was well understood and written down and codes were constructed to solve this evolution problem before one looked at exact solutions within this frame. All right. Actually, the motivation to go into these exact solutions was nothing really to do with gravitational wave theory. It was to do with code development. Right, codes have been developed for this, but in some senses they didn't work, and trying to understand was impossible until one had an exact solution. So that's why the exact solutions were developed. What one wanted was an exact solution representing gravitational waves, and then once you've got that, you can compare your numerical evolution to the exact solution and sort out the problems. So that was the motivation for doing this work. Alright, so what we do now is we construct exact linearized solutions about Minkowski. So we write WC equals 0 plus W. All these quantities are small quantities, and we just ignore everything of order epsilon squared. And Einstein's equations going from, well, to write down Einstein's equations in full generality, I'm going to take the rest of the transparencies of this talk and hopefully with understanding. Okay, the linearized version we can write down in very simple form, and one can then see how one has a system of equations that can be solved. All right, we also use the generalized angular gradient operator F. Again, I won't say more about it. One can just say that F is a generalized angular gradient operator. In some contexts, it's QA d by dA.
So that is like dd theta plus I cos theta dd phi.
Yes. Okay. So then the evolution equations take this form, and the constraint equations take this form. All right. So what you've got, and in a way, what will happen is the key equations are the evolution equations, and then the constraint equations are the usual idea of constraints, that if they're satisfied somewhere, they're satisfied everywhere. So what we use them to do is to fix certain constants, and then it will turn out that they're satisfied everywhere. So these are the equations that matter. Right, and since they're linear equations, one can make the normal type of ansatz that one makes when one's dealing with a linear wave system, and one makes this type of ansatz. So first of all, that you've got a causal sine a sinusoidal time behavior, and then the angular dependence is essentially spherical harmonics, where these Z1, Z and 1, 2 are obtained by applying this angular gradient operator to the spherical harmonic. Right, these ZLM they're the real spherical harmonics, so they're 1 over root 2y plus iy. All right, because one wants these quantities, say beta and w, to be real, and it just introduces mode mixing if you work with the normal spherical harmonics. So they're just the real spherical harmonics. Right, and then what happens, you can make that ansatz, put it in, and the angular and time plot disappear, and all you're left with is an equation in the radial direction. Okay, exactly the same as happens when you're solving the wave equation. All right, but the remarkable thing is that you can then use the constraints to eliminate integration constants. All right, because what happens is this equation will have 2 integration constants and then another 2 when you integrate that. And then you have another integration constant from the, 2 more. Beta naught, which will turn out to be constant, and from W naught. You can fix 2 of these constants from these constraints, and you end up with a simple polynomial solution for the radial part. So what we've ended up with is we've got a complete linear solution to the linearized Einstein equations, that in the angular direction it's essentially a spherical harmonic, in the time direction is sinusoidal, and in the radial direction takes simple polynomial form. Okay, and that makes it something that's really easy to work. Right, so the first application was sorting out the code problems. One can write down cipher and use exactly, and well, I won't go more into it. I mean, that was just why these solutions were set up in the first place. We could also apply this in this language to the, I mean, this isn't going to produce any new physics, but it's just useful to have things in this language. I mean, we just get out to lowest order the quadrupole formula. But, so you take two particles each of mass n, I mean, put them in this configuration here, they're going around each other. And so what we say is that we regard the two particles as generating matter shell, and what we can do is because what we've just we could write down the density as taking that form, or up from that physical problem, and then decompose that into spherical harmonics. All right, you're still going to get the delta R function, but that's fine. And it will turn out that things that dominate everything are the L equals 2 as one would expect. But one can also work out if one wants to all the higher order spherical harmonics. So you work out something specifically for rho 2, and that then enables you to completely solve the problem. Right, and what you end up with is a formula for the gravitational radiation or the gravitational waves, which reduces to the quadrupole formula in the Newtonian. And you can also get out the higher order multipoles, as many of them as you want. Okay, so that's really the sort of background to what I want to talk about. And now let's go on to the actual problem. So to sit a space-time in standard coordinates takes that. Right, so the first thing we need to do if we're to apply this formalism is to translate this metric into Bondi sets. Okay, and then, so lambda is the cosmological constant, and alpha is root 3, is root lambda over 3. Okay, so it's just going to be more convenient instead of writing square root all the time to work with alpha. So essentially alpha is square root of lambda, and alpha squared is alpha. Right, so that's the coordinate transformation that's required. You apply it, and the metric takes this nice simple form here when you do that. All right, and
I don't understand. Digital space is 3 cross R, topologically.
Is what?
Topologically, 3 sphere cross a real line.
Yes.
But the coordinates that you are writing do not. How do you change
No.
to Bondi coordinates, which is not compared in 2 directions?
No, I mean that. Yes, that's true. So
But
in
I don't see
these,
the first line. I see T. Suppose that is a R.
that
But that must be 3 sphere metric. You go square.
that row is R.
But then this is not a S3 cross R.
This
Digital
is
space is S3 cross R. S3. So it's compact. Topologically,
no, but this is the standard
S3,
form.
S3 is compact, cross is a real line. Is the digital space. It is a space like form in 5 dimensions. No?
Yeah, look, you can
I don't understand that, but this is a standard digital metric.
There
This
must
is-
be horizons in this formula.
Yes, there are horizons in this.
This cannot be global coordinates.
No,
No, these are no, these are
no, we're not going to work with. We're not going to work with global coordinates because we're only interested in the part of the universe that we can see.
Yeah.
So we're not using global coordinates at all. I don't care for this about
What I insist on is that this metric does not describe by itself. It's the de Sitter space.
No, it does. Not the entire decision. It describes a patch of
But
decision.
if I take all of the universe and take a little bit and put Euclidean
No,
metric,
no,
I cannot say it describes a patch
No,
of
but
it.
I don't want to do that. I'm
Euclidean
only,
is only a tangent plane. No, it's not a tangent plane, but it's a one representation of the Sitter matrix.
yeah, and I'm only interested in the part of the universe that I can see.
Yeah.
The rest is irrelevant
Yeah.
because I can't measure it. All right, so we end up with the metric in this form here, and in a way that we end up with something simple is actually quite remarkable. Because the only other cases where one can do that are Minkowski and Schwarzschild. There are no other known simple solutions. Even Einstein de Sitter, which is the simplest cosmological metric, if you try and translate it into Bondi-Sachs, you end up with something that has to be,
But
part of it has to be evaluated.
The very remarkable thing is that this is the Schwarzschild equilibrium, because the de Sitter and the Minkowski doing is both are maximally symmetric
Yes.
spacetimes. But the Schwarzschild is not maximally symmetric, it's inhomogeneous spacetime. And yet it's
Yes.
that is something remarkable. But de Sitter falling in with the Minkowski is quite understandable.
Right. And what we'd also need for this is how the full velocity is going to turn out to be important. In Bondi-Sachs coordinates, it might take. I mean, this has been set up so you've only got one parameter, V0, and then this automatically satisfies or VA, VADP, GAD equals zero. It equals -1. Right, and then that would be related to, in the de Sitter coordinates would take that. So if you want to talk about what you might call the preferred de Sitter observer, for whom that's 0, that means that V0 is equal to 1 over 1 plus RA. All right, so one just follows the same procedure to linearize, except the Einstein equations are now different. Did you know that I take into account the cosmological constant term? And what's also remarkable is that the equations can be solved exactly, and we again end up with simple polynomials, which means that things can be handled. All right, so these are the same sort of, these formulas are the same as before, except where there's an alpha. So one sees that one gets that new term, that new term, that new term, etc. So that basically the same as before, but with these alpha corrections. All right, and then one could also do this problem just within de Sitter space-time instead of the Minkowski background. What happens to the for the case of two equal mass objects in circular orbit? So this is the same as before, all right, but except for the new terms involving it.
So what is the value of mu?
This is the frequency. So for the physical problem, it would be it's the frequency of the gravitational wave, so it's half the orbital frequency.
So that is actually very small. Mu.
It depends what objects you're talking about. If you're talking about two black holes that are about to collide, no, it's not.
Okay.
And that's the only thing that you're going to measure. As far as talking about LIGO is concerned, you're only interested in the case when nu is somewhere between about 20 Hertz and 1,000.
Okay.
Otherwise you can't see.
But alpha is going to be very small for our
Yes,
non-linear.
yes. And as far as whether this affect's relevant or not, I mean that's the crucial issue.
Yeah.
Could it have some relevance in the process in early
Sorry?
universe? Could it have some relevance in the processes in early universe? Well, for
That's
example,
certainly possible. I mean, they're different questions one can ask.
larger value of cosmological constant, for example.
Yes, and then if you're talking about distances that are larger than the cosmological, it will turn out that, I mean, you'll get a formula that depends on lambda, the distance to the place, and the frequency. All right, so what we have is that we now want to talk about the gravitational radiation. This is where things get a bit subtle. Right, so if the background is Minkowski, it's easy. You can regard, well, we know, so the metric involves three arbitrary constants. We know that two of them must represent gauge freedoms. Right, and in the case alpha equals 0, one can simply impose the Bondi gauge conditions, beta naught equals 0, J naught, and the limit as you go to infinity equals 0. The metric tends to be explicit Minkowski form, and the R minus 1 part can then be interpreted as the wave strain. And that's very standard and is easy. Okay, in the de Sitter case, this doesn't work. One has to deal with the gauge freedoms in another way. It's not possible just, if you try and, you can't do that. So, in the asymptotically flat case, gravitational waves can be described by the wave strain, the news, or the Newman-Penrose quantity psi4. A Newman-Penrose quantity, which is going to be important here, is the Weil tensor dotted with certain null vectors, which I'll describe. And these descriptors are related. That a key point is that the magnitude of gravitational waves decays as R minus 1. So that this quantity here is independent of R. I mean, in a way you can regard this result as a necessary precursor for Bondi's news, gravitational waves equal mass loss theory. If you don't have that, you haven't got a hope of getting integral S n squared is equal to the mass, is equal to the change in the mass. So we're going to investigate two things. First of all, the form of the gravitational wave, and for a de Sitter space-time, to investigate under what conditions energy conservation occurs. All right, so the most convenient way to do this is by constructing psi4. And specifically in the background space-time, the de Sitter space-time, you can work out what this null tetrad's going to be that's required to work out psi4, and it explicitly takes this form. Right. Now we come in a way to a key point. The Weil tensor of de Sitter space-time is 0. Okay. And what that means is that if we're actually talking about in the real space-time, we should actually, in terms of this n, l, and m, there should actually be order epsilon corrections to it. Okay, but because C is order epsilon, we don't care about the order epsilon part of n, l, or m. They're irrelevant. So what one can say is that this quantity is gauge invariant. And working with gauge invariant quantities is A, much easier, and B, avoids mistakes. I mean, you can actually allow for the gauge quantities, but it's tricky. And when things are tricky, you're likely to make mistakes.
So when gravitational wave is present, then the Y tensor is some epsilon times the Levi-Civita tensor, is it?
The gravitational wave we would represent by, well, we're going to say more about it, okay. Because that's not the whole story. Okay. It's just mathematically the most convenient way to represent it is in terms of the Weil tensor. So psi4 is standard as a description of the gravitational wave. All right, so we can work it out, go through the algebra, work out psi4, and we end up with this quantity, which on the face of it is very nicely behaved. Okay, we've got the 1 over r dependence, which we would expect, but there's certain questions that we need to ask. Okay, well, the correction is only going to be significant when u squared is less than order alpha squared, all right, which means corresponds to a wavelength of several gigaparsecs, and there's no way LIGO is going to see it. All right, but the first question we need to ask is, what does LIGO measure? LIGO doesn't measure the violence. What it measures is it measures wave strain, and that can be regarded as geodesic deviation. And geodesic deviation is given by a formula involving the Riemann tensor, not the Weyl tensor. Now, I mean, this is not normally an issue because in a vacuum space-time, RAB equals, and lambda equals 0, RAB equals 0. So they're the same, so who cares? But here, that's not the case. Okay. In de Sitter space-time, and this is something that has to be checked, the result is still true, since the difference between them is between Weyl and Riemann is just a product of metric terms. Right, and it's a product of metric terms with this lot of vectors. And the only pair of vectors whose inner product is non-zero is Ln. Every other inner product is 0. Right, and so you then check the Ln and the symmetries, and they vanish in. Okay. All right, so it's justifiable to regard gravitational waves as properly described by this gauge and varying quantity. For a physical interpretation of gravitational waves, we need to do rather more than psi4, because we're using, in a way, coordinates that are a constant r, and in these coordinates, being a constant surface area distance from your source means that you're accelerate. Right, and LIGO's not accelerate. LIGO's in free fall. Okay, so we need to allow for that. Alright, so the way to do it is to take the time derivative with respect to the proper time of the observer of LIGO, and then you expand it out and we'll get these terms here. Well, I mean, that term you'd obviously expect. That's just really the relationship between the coordinate time and proper time. So that's exactly what you'd expect. This term will turn out is irrelevant, because when psi4 involves leading term is 1 over r, you differentiate that, that's going to give you 1 over r squared if it disappears. Right. The problem is this term here, because when you work it out, when you work out d tau dv norm from the geodesic equation, you get that r. Right, and this is the cause of these interesting effects that I'm going to discuss. It's that r. Expression is rather long, and it's leading order in r. When you work the whole thing out, this is what you get. So you get this term here, which is independent of r. So you can then work out the total energy crossing a 2 surface, r equals u equals constant, which is the quantity you want to keep constant. And what you get is these v0 squared and then this r squared term here.
So this is application of the Landau-Lifshitz pseudotensor. How do you get the energy flux for the gravitational wave?
All right, from the, so the energy flux would come, it's a matter of working out this quantity, which is then the first derivative of psi. Yes, so the news, the news is the integral of psi.
So this is different. It's different, but this is not the pseudo tensor or that sort of thing.
No, so this is going back to, this is actually using the notation that, and the language that Bondi uses, is news equals mass dot speed. Okay. And the news function is the integral of, the time integral of psi.
So this is the flux and the asymptotic.
This is the flux over some surface.
Yes.
And what you want is for that to be independent of the surface.
Right.
So the total energy, which is the integral of the news, takes this form here. Right, and the only way to get this independent of R is if you set V naught, you've got the freedom then to choose your set of observers. Alright, so you can choose a set of observers for which V naught falls off at the right rate, and then you can achieve that. And then you would have that the full velocity of the observer in Bondi-Sachs coordinates would have to take that form.
But for any other observer, it's like proportional to R square.
Yeah, I mean, what we're going to do is we're talking now about a set of observers in Minkowski space-time. I mean, the simplest set of observers is those who are any set of observers in a sphere who are at rest with respect to the origin. For them, energy conservation applies. Here, you've got to choose your velocity depending on the value of R.
But the preferred observer in the de-Sitter space-time
We'll
will be the
talk-
cosmological observers, for whom the r theta phi coordinates are constant.
Yes.
So-
But I'll talk about them. Yes, obviously that's a question I'm going to answer in a minute. All right. So for observers in free fall, now you've got this problem. Consider the example where the constant d is fixed by the condition physically observers close to the source or at rest relative to the source. But then this just makes things a bit simpler, and the velocity of the observer would have to look like that. Thus, the velocities depend simultaneously on position and wave frequency. So if I've got a monotonic wave, I can do it. But if the wave frequency changes, as happens during an in-spiral, then the observer's velocity would need to be adjusted. So the observer has to be accelerated. And I mean, that's a key point. You can do it, but the observer's going to have to undergo an acceleration as the wave changes, because in any real event, that's what happens. So abandoning the idea that the observers should be freely falling, we can set V naught equal 1 everywhere. And what that means is that the observers for whom energy conservation, right, because then that term disappears. Each observer must then be accelerated. So the natural de Sitter observers are in free fall, and so do not constitute a set of observers for whom energy conservation applies. So that's really the conclusion. And what does that all mean? Okay, that. I think it may mean something interesting. I mean, because it is counterintuitive. Okay, because I mean, it goes way back since before Newton. The key observers were the inertial observers, and one regarded them as special. And one also, a fundamental idea in physics is that energy conservation is special. And and then the idea that energy conservation applies, you've got to choose one or the other. You either abandon your principle of inertial observers or of energy conservation in order to write something down. And, well, the real universe does seem to be accelerating. The expansion seems to be accelerating. So, this may say something interesting about fundamental physics. What happened? I mean, these are questions that I think still have to be explored. But I think this is an interesting result that needs to be thought about.
So, can you say something about? So, can you say something about how the expansion of the universe looks to these observers? Is it the same as?
What to the Bondi-Sachs observers, those observers who are at fixed surface area coordinate, I mean, from their point of view, they're resisting the expansion of the universe, so the only way to do that is to have some force that's accelerating them inwards. Okay. The observers for whom energy conservation applies, okay, so they, all right, so if you're talking about a monatomic source, all right, so for them we've got okay. I mean, so what it's saying is, okay. I mean, what are they? Okay, so first of all, they're not the natural de Sitter observers.
Yeah.
Okay, I haven't actually shown that, but one can translate that back. They're not the natural de Sitter observers. Well, in a sense, they can't be, because this formula depends on the wave frequency.
Right.
So, but in terms of what their velocity, I mean, it'd be easy enough to work out, but I haven't done so.
Sorry.
Okay.
May I intervene with
Yeah.
a comment, not my comment? In Bengaluru, Rafael Sorkin was there and Joseph Samuel was there, and the following question came up. And the answer was, let us say, not in de Sitter space. The reason I was asking the question is, this is not a question about the experiment. Okay? It's a question about the theory. Okay? But in the theory, for example, in Einstein gravity, every observable must be diffeomorphism invariant. Exactly. Without doing any calculation. Okay? But if it is asymptotically flat, one can argue that it must be invariant under diffeomorphisms which are asymptotically trivial. So you can say that the gravitational wave is one, which is an equivalence class which you look at infinity, it should look like a Minkowski waveform. You can give a meaning. But de Sitter space is not asymptotically flat. Okay? So I do not know what is meant by a gravitational wave in de Sitter space. I simply do not know what it means. Okay? Because if everything is diffeomorphism invariant, we cannot even define a wave. What does it mean? Okay? Now, it seems to me that all these problems are arising very much like in Rindler-Bedge. If you try to take space-time translations, it doesn't make sense. So everything that comes out by that concept is an artifact of coordinate systems. Okay? It seems to me, because I do not know how a wave will be described intrinsically. No, forget about, I am not talking about experiments. Okay? Theoretically, everything must be diffeomorphism invariant. Is this diffeomorphism invariant? Not mathematically. Not mathematically.
Because of these issues,
Yeah.
because of these issues, I mean, because it's impossible to define. But because it's impossible to define
Energy.
a future non-infinity.
Yes.
Yeah. The question that I'm asking is not that. The question I'm asking and that's why I worked it out very specifically, is what does LIGO see? What does LIGO see?
Experiment, what is it?
That I do not know. There is a discrepancy between what we know about experiment and what the theory for discipline says.
So that's the question that's being asked.
Yeah. No, but Nigel, how do I construct this observer? Because this looks to me I can't construct it unless I know the frequency of the wave.
Absolutely, you can't.
So this means these are not real observers. This is why I can't actually construct them.
No, this means that for general observers, the energy conservation doesn't hold.
But the point is, DC space does not have space-time translations as isometries. The SO41. It is something different.
So that's precisely the point, because there is no time-like killing vector.
Exactly.
There is no conservation of energy.
No.
But the fact that there are free space translation killing vectors, one can show that
It does not have. No, it does not have that.
space killing vectors.
No, the group is SO41.
No, it's
that
maximum.
three-
It's
If you
maximum.
do this restrict regions and introduce, but the exact symmetry of the DC space, naturally, of course, it may not even be there, but the natural metric on this is SO4. It is the space-like hyperboloid in 5 dimensions.
Yeah, but suppose you make a local statement, there are killing vectors. So the killing vectors, 0, 1, 0, 0, from the killing vectors we know that the physical momentum must fall off as the scale factor.
Cannot be
1 over scale factor.
exponentiated. The exact symmetry is SO41.
But
I'm talking more
it has a
local.
maximal symmetry.
Huh?
It's a maximally symmetric.
That is SO41. It has 10 generators. It is maximally symmetric.
Yeah.
But this translations is not a subgroup.
Yeah, transverse is not. That's right.
So we cannot define momentum globally.
Globally,
Global.
So what do you mean by local momentum? That
No.
depends on your conventions. And so.
there is a horizon, right? So inside.
Horizon only for discipline only because you introduce this like a Riddler wedge. You introduce this.
Yeah.
Horizon is already there.
No.
No.
Horizon is
SO41
physical
is-
horizon.
It is not. It is a what is it? Observer dependent.
It's observer dependent.
That's the difference.
But supposing regarding LIGO observation, if we ask the following question, that how does the proper distance between two events, the two endpoints, change when you have this solution? That's a invariant object.
That kind of thing can be
That's-
asked.
So that can be answered.
You can ask questions like the gravitational wave is coming and is coupling to the pendulum, and then you can form an invariant and you can ask the geodesic distance. How it is. All those things can be formulated, but then you can call it the wave. The wave is a name, no? So we can call it the wave. This is what I mean by wave in DC. You can go, okay? Because that is what you see. That would not be troublesome. But classic Minkowski, asymptotically Minkowski ideas, I don't think apply here.
Yeah.
Well, that's precisely the point.
But I don't
That's
see-
why he's considering that. Yeah.
No, but
So how-
I am uncomfortable with this kind of analysis.
No, it's no. Point is, no. Not that he is completely comfortable with this. The question is, but the question is relevant. This question has to be addressed.
Yes.
The question is relevant. It has to be addressed because we live in a
No, but Naresh, that we live in a digital universe should be made with a qualification.
Yes.
This is only at lens scales bigger than 350 megaparsec.
No,
On
no,
local
no,
scales there are
No,
inhomogeneity, where gravitational waves will be produced.
But you see, the point is asymptotic limit. You will have your 350 megaparsec.
Yes.
Yes, right. So that's why I mean asymptotically it is a digital space. So that's why the question being asked.
No, but
So whether the answer we are getting is right or not, it's a question.
Shall we break for coffee or you want to continue?
No,
15 minutes. That is 11:40, 11:55. See, my heavy work will be over with 2 more.